Welcome to Module 4. This week we're going to be talking about geologic structures and deformation regime. We are going to introduce you to Chapter 1 today. With the key factors that we're dealing with are some of the depositional structures, unconformities. I want you to read through most of this. Let's take a quick look at the textbook. Again, I'm going to be concentrating largely on the first part, which relates to sedimentary structures and how they relate to geologic structures, but definitely read through. I'm going to hit on some of these things in terms of salt structures, igneous structures, impact structures a little bit, but please read through this entire chapter. It'll help you to begin to learn the terms that we use in structural geology and start to understand some of the things that we have to know before we go out in the field and start mapping. So let's get to it. Start off with a quote, and this is related to non-tectonic structures. And although it talks a little bit more about metamorphic rocks than I want it to, it really ties back into what we have to do in structural geology. So let's just read through it once. It has been said that stratigraphy is the basis of all geology. This is true of metamorphic rocks as well as the sedimentary rocks. Cognizant of the importance of petrography, physical chemistry, and structural geology, the investigator of metamorphic rocks should nevertheless give more adequate treatment to the fascinating problems in stratigraphy, sedimentation, and paleogeography that await solutions in interesting rocks to which, perhaps foolishly, he has dedicated his scientific career. Now again, this focuses on a geologist who is focusing in the world of metamorphic rocks, but it really ties back to the importance of stratigraphy and the importance of stratigraphy to structural geology and the understanding of sedimentation, paleogeography, as we try to rebuild the geologic past. So we're going to spend some time talking about primary structures. If you've had sedimentology, I think that's Geology 308, you may have already seen some of this. You'll have seen some of this discussed in Geology 101 and Geology 105, perhaps in Geology 201. But we really need to get a feel for what some of these primary structures are. By definition, primary structures are those structures that originate during the formation of a rock. So as sediment is being deposited, there are certain types of sedimentary structures that are being created. And it's not just sedimentary structures. This also happens within magma, within volcanic rocks as well. But they have to form prior to lithification in sedimentary rocks. They also form during flow and late stage congealing of magma before and during final crystallization in volcanic and intrusive igneous rocks. We're going to look at some of these. Again, particularly we're going to spend time on the sedimentary rocks. Why do we study sedimentary structures? Well, first we must know something of the form and fabric of rocks before they were deformed. If we don't understand what can happen to rocks before they're deformed, we won't be able to understand what's happening during deformation or after they're deformed. They can also be a guide to strain. We're going to see this later in the semester as we start talking about stress and strain. And we'll be looking at some of the sedimentary or metamorphic or igneous rock features, mineralogy features that we can use to help us understand strain. It's also a guide to facing or Jungian direction in a sequence of rocks. We're going to spend significant time talking about understanding facing and Jungian direction. So let's start off with this idea of stratigraphic facing, or in other words, which way is up? The pictures I have here are in the center, ripple marks on a beach. Up here in B, we have large crossbed sets in a sandstone. This was likely a sand dune at one time before it lithified into a rock. Down here in this corner, we have pillow basalts. Pillow basalts form as lava flows into a body of water. So why do we care? Why do we need to see these primary structures? Well, again, to understand primary structures is to first figure out and how can they help us to understand deformation caused by plate tectonics. So many of you who have come into the Zoom meetings have seen me draw a picture similar to this. As you were working on your block diagrams, one of them talked about overturned folds and an overturned bedding and related to a strike and dip symbol. And this is what I typically drew. A set of horizontal layers. Again, this is the law of original horizontality. If every layers are laid down horizontal layers, law of superposition, the oldest is on the bottom, youngest as we go up. And if we add a compressional stress, and we're going to push this together, and any of you can do this. You can do it with a piece of paper on your desk. If you have a wood floor in your apartment or your dorm room or at home, you can do it with a throw rug. All you have to do is put compression on it. You'll see these things starting to bend. And you're basically forming antiforms and synforms, these hills or valleys that we're all fairly familiar with. But what happens when you continue to add the stress? When that happens, you tend to push these folds over. They become from symmetrical to asymmetrical to eventually overturned. And what we see are beds starting to fall over on themselves. And so what does that mean? It's overturned. And I'm going to try something here. Let me grab a pen. If we look at these units here, I can put in little arrows. In these units, the rocks are still facing upward. Everything, if I were to look at the fossils in these rocks, if I were to look at bedding in these rocks, everything is facing upward. But what happens when we get here? We're starting to fall over. This is starting to flip. And by the time we get over here, these beds are now facing upside down. So if we look at an overturned fold in nature, as we see here, this is the axis of the fold. You see where it's bent here. Another axis of fold here. So this is just our throw rug that we've pushed a little bit too far, and it's fallen over on itself. We can follow the dark band around. And we know up here, this is right side up. This is our normal horizontal bedding right here. Everything is right side up. But as we move along and we trace this across here, we see by the time we get around the curve and over here, everything is upside down. We go to Gibraltar, we can take another look of a partly overturned fold. Again, starting off with horizontal layers, compression. We start folding the rocks. In this case, we're adding a thrust fault, which is cutting through the rocks and creating drag, and we're seeing the folds overturn. And this is the example we're seeing here. We're seeing this overturned structure. So up here, beds are right side up. Let's go ahead and get our pen again. These beds are right side up, facing upward. But as we get over here, what's happening? They're starting to turn. And eventually down here, they're upside down. This is the upside. And over here is the downside. So let's just imagine if we erode this away, and I'm going to put in an erosional surface. So all of this up here is gone. We can't see this anymore. And here you are, walking out here as a geologist with your hard hat on. And you're out here in the field, and here you're starting to take some strike and dip measurements. Well, we know that it's dipping back this direction, striking toward us. So our strike is coming out of the screen in this direction. But if we map this as everything being right side up, our geology and our interpretation would be completely wrong. We have to recognize these beds as being upside down. So if you're a geologist out in the field, it's key to understand facing direction. What is right side up and what is upside down? Because we don't get to see everything. We are the CSI of science. We go out, the earth has done something, it's left behind some evidence, but we have to use that evidence to start with our data collection to start to understand what actually happened within that area sometime in the past. So the first thing we need to learn about, or we have to understand, the primary structures is bedding. We have been working with bedding. In our lab number 2, you actually spent time drawing in beds. You did both a cross-sectional view, you did map view, you started drawing in bedding contacts and bedding planes. But let's spend a little bit of time actually thinking about what these beds are. So when we talk about bedding, we say it's the most common characteristic and most diagnostic feature of sedimentary rocks. It's the first order reference surface for most structural measurements. So what we want to do is we want to find the bedding. Oftentimes in structural geology, we are mapping sedimentary rocks. We also map metamorphics, but metamorphics can also demonstrate bedding. And we also map igneous, which can have, if we're talking about volcanic rocks, can have bedding, but doesn't have to. So, but let's look at the bedding here. We have nice horizontal beds. If we were walking up this slope, we could stand up here, we could put our hand on that, and we could trace that bed, just walk it all the way across. At the top and the bottom of those beds is something called a bedding plane. It's the mechanical zones of weakness that form in primary sedimentary environment. So if we went to the very base of this bed here, we put our hand on it, that's a bedding plane. We can stand on this dipping unit, and this flat surface is the bedding plane. We put our compass on the bedding plane to measure strike and dip. So again, going back just so we can review a little bit, get my pen again. If we're talking about the right-hand rule, this bed is dipping in this direction. So we would have to be looking in the direction of strike in that direction. So our strike and dip symbol on here would go like this. And that's what we'd be mapping on our bedding plane. Of course, we transfer that onto our topographic map, which then we build into a geologic map. But those are the bedding planes that become extremely important in our analysis for structural geology. The other thing we're interested in is what's happening within the beds themselves, because that's going to help us understand something about facing. So when we look at a cross-sectional view of a sedimentary bed, so in this case, we have two sedimentary beds, 1, 2. This would be a bedding plane that's running across, and also is called a contact. And in this case, what we're seeing is the demonstration of graded beds. This is where the coarsest grain material settles out at first at the base, and then the finer materials settle out on top of it. And this is just a series, in this case, of graded bedding. So when we're looking at facing direction, if we recognize a finding upward sequence of graded bedding, we can likely say that this is the bottom of the bed, this is the top of the bed. Now, there are exceptions. There is a such thing as reversed graded bedding. And so you often have to look for other pieces of evidence as well, besides just graded bedding. As a geologist, we always have to have combined pieces of evidence. We can't go with one thing. We never go with one. We go with multiple things to understand what is actually happening. Also in cross-sectional view of sedimentary rocks, particularly sandstones, oftentimes, and sometimes limestones, oftentimes we see cross-bedding. Again, this is a primary sedimentary structure, forms where sediment grains are transported by water or wind and produce moving mounds or dunes with inclined laminations within an individual bed. So if we look at this line right here, that would be a bedding plane. And this is one set of sedimentary cross-bedding within that bed. And we can look at each one of these as separate little beds within, and within them we have cross-bedding. There's a variety of types of cross beds. Again, I'm going to show you these, but you'll get more of this information when you take a SED course. But you have normal or trough festoon bedding. You have torrential or planar cross bedding, ripple cross laminations, and hummocky cross laminations. We're going to take a look at each one of these as we go through the slides. First thing I'm going to show you here, of course, this is a large dune created by motion of sediment and moving the dune. We're going to take a moment, and you can click on this if you open up the PowerPoint that I've supplied for you, and you open this YouTube. I'm going to go ahead and zap out of here, and we're going to go get it, because I have it already downloaded and all ready to go. What we're going to do here is we're going to look at a water tank. It's filled with water and sand. Sand is the darker grains and light grain sand. And we're going to look at what happens during dune migration. And forgive the screen. I don't know what happens to their video here, but it takes a moment for it to get started. Your current is coming from the left to the right. And already we're starting to see the migration along this line here. You can see where the darker grains tend to be lining up, and that's cross bedding. We're starting to form cross bedding as we settle out along the front edge of these dunes. So this is that large dune. Current is moving across, sediment is being carried and draped. And as you can see, the sediment collapsing down over the front as the entire dune migrates from left to right. Now in this situation, we're really creating planar cross beds, which are very straight cross beds. And one of the things we're going to find, if you look down here at the base, oftentimes, and they zoomed out, there we go. As you look down here at the base, these things will start to curve and flatten at the base. That will become very important in our understanding of what direction is up as we look at these cross beds that have been preserved in a sandstone or limestone as a rock. Okay, I think that's enough of watching that. Let's go ahead and go back to our PowerPoint. So the first type of bedding I will look at is trough cross bedding. Okay, it says produced by the downward flow migration of lunate dunes in both subaqueous and subaerial environments. So subaqueous means underwater, subaerial means above water on dry land. So this would be a desert environment. This would be, of course, like a river, or it could be ocean currents. And what you're looking for, and the flow here is from left to right, what you're looking for is these curved shaped dune features. That's what lunate is. And what happens is the sediment migrates across this, and of course it's still falling over the edges. But oftentimes what is preserved in very small sections are these very curved, bottomed type structures. Or in a very large setting, you can get these very large trough beds, and they're basically forming a trough. If you can find these troughs, it's a great way of figuring out the direction of flow in an ancient river system. Here's an example of a lunate dune. Here's the flow direction. So it curves down flow. And if we take a cross section of that, we're just basically cutting off this side and exposing it. You can see how the grains migrate up and then down this lunate dune form. Planar cross bedding, which again, this is a better example here of a large planar. You can see a very straight edge. And this is really what we just saw in the water tank experiment, the formation of these what are called planar crossbed sets. And it is just what it says. It's very planar. These dunes are fairly straight, and instead of troughs, we're forming fairly straight crossbed sets. And again, what we see is at the top, they're very sharp, and as they get down to the bottom, we're going to see that they start to flatten out. And this is an example here. In this case, the flow is from right to left, and what we see are tangential force sets. So a tangential force set is this curved part of the dune as it comes down to the base. So if we see the curved part, we see that tangential curve, that force set, that's always going to be the bottom. So again, I'll get my pen. We know that this is the bottom, this is the top. So this is the top of the bed, this is the bottom of the bed. And we see it again up here. We see this nice tangential curve, and it comes up. And so this is the top, this is the bottom. So our facing direction, or up direction, is like that. So if we find that upside down, we know we have an overturned bed. And therefore, in terms of our structural geology, we have to start thinking of the mechanisms that could result in this type of the beds being folded and then flopped over and overturned. Continuing with primary sedimentary structures, we're going to get a little bit smaller with a little bit slower flow than what we saw with our cross bedding. And this is ripple cross lamination. And basically what it means is we get the formation of ripple marks on the surface, but each one of those little ripple marks are similar to the dunes we saw before. And we really have two types. There's current ripple lamination. These are bed forms generated by unidirectional currents. And that's what we see here. We see a shallow side and a steep side, shallow side and steep side. So our flow direction is from left to right. Down here, we see something similar, shallow, going to steep, and they crawl over top each other. So they kind of oftentimes we call these climbing ripples because they actually climb over top of each other and migrate onward. Oftentimes, because these are rounded on both sides, it's very difficult to tell facing direction. If we see this type of I can't tell you if I turn this upside down, which way was up. If we look at wave ripple lamination, these bed forms are generated by multidirectional currents. Oftentimes they are fairly sharp at the base. They have a trough and a fairly sharp base. Fairly sharp base. I'm sorry, a trough, a fairly sharp crest. The crest is sharp, the trough is rounded. And so we see that down here. We see a sharp and rounded, sharp and rounded between there. And so with this, if we see that sharp crest, the sharp crest has to be facing upward. If it's upside down, we know the bed is upside down. So facing direction again can be used to help us understand facing direction or which direction is up. Hummocky cross stratification is a little more difficult to see in outcrop. It sometimes mimics or is hard to tell from basic cross bedding. You have to have much exposure. Tends to form in deeper water, oftentimes associated with storms. So it consists of what are called swales, the low areas, and hummocks, which are the lumpy parts that stick up over top. So there's a swale down here coming up to a lump up here, or hummocky. It's undulating cross laminae that cut into each other as curved erosional surfaces. It can be useful to determining facing direction if you can identify it in the field. You can identify this hummocky cross stratification. We know which direction is up. Tends to have a sharp base and a rounded top. Another type of primary structure that we love to see, and you'll actually see a lot of this if you go out anytime it rains and there's a little bit of mud on the road or in the ground and the sun comes out, you'll start to see the formation of mud cracks. Well, mud cracks can be preserved if those mud cracks are then buried. And so we end up with the cracks being filled with sediment. So again, if we see mud cracks, we know that which way is up. Where we must be looking at the upward face, or we can tell from the mud crack position. Form when fine sediment is exposed to the atmosphere, quite useful in determining facing direction. We can also oftentimes see, and we can see it a little bit here, we see raindrop imprints. Down here we see better raindrop imprints. These are indentations. So again, if we see the indentations, we know they were formed by a raindrop falling, we know which side was up. There are also types of sedimentary structures called soil markings. These can be created by current flow. They can be created by dragging sticks along a bed. But basically what they do is they're formed by an object moves across bedding surface or as currents scour a bedding surface, creates concave up feature and good facing indicator. These are flute casts. These are caused by current flow. In other words, they're typically of a indentation dug into the mud. And basically, we're looking at the bottom of a bed here. So if we find these and they would be facing upward, we know the bed was upside down, because these typically would be found, you'd have to find them on the bottom of a bed on that lower bedding plane because they're going to be preserved in the lower part of the bedding plane. Here you're seeing little groove marks created by a tool. In this case, it looks like a stone bouncing, or a stick could be dragging. and you end up with this concave. Again, this is going to be carved down into the muddy sediment or fine sediment below and then covered up. And so if we see this, we can tell which direction is up. Scour marks. Scour marks, again, are erosional surfaces that are cut down into the sediments below, and oftentimes they're small channels. And this is a nice scour surface that's been cut down into the sedimentary layers below. So again, if we see a scour, we can tell which way is up. This has to be the bottom down here. This is the bottom, and this is the top. If we were to turn this upside down, we can't have an upside down scour. We have to turn that right side up again. And so again, we can use it to help us understand facing. There are some other types of primary structures that have to do with gravity and loading. And the first one we have here is a load cast. Again, this is a result of gravitational instability at the interface between a layer of water-saturated sand. This is this water-saturated sand before it's been lithified. This is lithified now. And an underlying mud after deposition and dewatering. Dewatering means that the water is starting to move out, and what we end up with is horizontal layers of sand over mud, and gravity is squeezing the mud, and the mud is being forced up into the sand, and you end up with these big rounded features, which are called load casts. We're going to take a look at these other structures, which are called flame structures, in just a second. And we're starting to see the beginning of flame structure here, where the mud is pushing up into the sand above. Again, if we see this, we know that can't happen the other way around. It can't happen with mud on top of the sandstone. It has to be the sand on top of the mud, so we know which way is up. And this is an example of the flame structure. This is a little bit finer grained than what we just saw. But again, we see these tongues. You can see how this looks like a fire coming up into the coarser grain material above, and the finer grained mud below. Again, if we see this flame structure, we know the sharp points are pointing upward into the sediments above. And we're not going to see that happen upside down. We can also look at trace fossils, tracks and trails. Up here is some nice example of tracks. Resting surface, such as a starfish. A feeding trace. This is the result of a critter called a zoophicus. And then there's this plant-like critter that grows these mounds, typically in carbonate muds, called stromatolites. Again, notice how they're curved. They're going to be curved and grow upward. And again, we can tell which direction is up. Using any of these things, we know which way is up by looking at the structures themselves. So again, looking at sedimentary rocks, looking at the internal structures associated with those sedimentary beds, we can tell the direction in which the rocks are laying and stratigraphically. And so we then can map correctly when we're in the field. There are also some primary igneous structures. I'm not going to spend a lot of time on these, but you should at least become familiar with them. There's primary foliation. This is oftentimes, and foliation is again an alignment of minerals. It's sometimes difficult to distinguish from tectonic foliation or foliation we see in metamorphic rocks. Compositional banding, which is what we see down here, which can result from crystal settling, differentiation, fractional crystallization, and from multiple parallel intrusions or flow processes that can flatten xenoliths. So again, these are some primary things that can happen during the time of flow of these igneous bodies. Some igneous structures that help us with facing. The first one up here in the right-hand corner are vesicles. The vesicles are formed by gas bubbles. So as a basaltic, for example, in this case, a basaltic flow starts to cool, the gas migrates upward. So where the gas bubbles are always at the top and lack of gas bubbles down at the bottom. So when you see the vesicle-rich area, you know which way is up. Contact metamorphic zones may be useful in determination of tops and distinguishing sills from flows. In other words, a flow will have a tendency to have a cooking zone at the bottom, whereas a sill will have a cooking zone at the top or could have a cooking stone at both the top and the bottom. This case was something called the Purcell sill, and this is a baked layer, a contact metamorphic baked layer above it. And so again, those relationships can help us understand which direction is up and how these, the geologic history of these areas. Down here are your pillow basalts. Again, your pillow basalts have a distinct look. They tend to be rounded on the top and flatter on the bottom. You see this, so the top is always round. So again, we can tell which direction is up within flow. If we see these types of rocks and we're out mapping, and if they're upside down, we say, whoa, this can't happen. We know that it's an overturned bed. So other gravity-related features that can happen are landslides and submarine flows. Okay, a landslide is prone conditions, or any place where you have a sloping surface, and you have parallel or bedding foliation or fractures, you can have a landslide. Landslide triggers earthquakes, overloading of slopes, high precipitation, undercutting, oversteeping of a slope. Any of these things can cause gravity-related features. Landslides may occur along the toe of an advancing thrust sheet, or any escarpment consisting of poorly consolidated materials, particularly in the submarine environment. So in structural geology, when we're looking at a thrust fault, we'll get into this later in the semester, we can see the evidence, there can be evidence in the field of landslides or these along the toes or along the fronts of these thrust sheets. We also find where we get gravity-related features associated with submarine environments. Two key words here that you should at least become familiar with: a listostrome. This is a melange of sedimentary origin formed by gravity sliding and slumping of blocks of largely sedimentary rocks down the slopes of the submarine escarpment. What is a melange? Melange is a large-scale breccia of mappable body of rock characterized by a lack of continuous bedding and the inclusion of fragments of rocks of all sizes contained in a fine-grained deformed matrix. A melange typically consists of a jumble of large blocks of varied lithologies. So again, these are things that we can see associated with structural geology, and things, if you're mapping, you may run into depending on the depositional environment and the conditions in which the rocks have been placed. I want to talk about a submarine feature, which many of you may have heard of before. These are turbidites. And your book does a decent job. This is an image from your textbook, so they do a decent job of explaining this. But a turbidite is a sequence of sediments. This is a deep sea flow, typically down a submarine canyon, and then out into the deep sea floor, where you're going to see graded bedding, a massive graded bed at the base, labeled, denoted by the letter A. Then you get planar laminae, which means nice horizontal laminae, and then you get rippled and convoluted. So current is slowing down as we get up here. And then you start getting into muds, because the finer grain current is slowed down more, and then eventually the hemipelagic muds settling out from the marine organisms as there's no longer any flow at all. And then there can be another avalanche, and this whole cycle can repeat itself. So if we see this cycle of sediments, again, we know which way is up. We know that the graded bedding starts at the massive graded bedding starts at the bottom, and we work up through the planar to rippled to turbidite to hemipelagic. And so we can look at a series of sediments within a formation to tell which direction is up by looking at how they relate to each other. I also want to, your book does a nice job of talking about salt structures, but let's at least mention them here. Salt structures, if you go down to the Gulf Coast, often a lot of the oil wells that are drilled in the Gulf Coast are drilled along salt structures. And many of the salt structures are also mined for salt, and you probably have used some of that salt when you have eaten whatever you like to put salt on, maybe some French fries. Formed in areas of thick layers of salt overlain by even thicker accumulations of sediments. So what we have is an environment in which salt is deposited. So it's going to be an arid environment without much other types of sedimentation. And then later on, that's buried by thick layers of sediment. In the Gulf Coast, we have the Jurassic salt beds, salt flats, that were then overlain by younger sediments of sand and mudstone. And that's what has resulted in very thick or very tall and large salt domes and salt bodies within the Gulf Coast. Salt changes and moves because of density inversion. The low density salt, which is around a density of 2.2, that's supposed to be an equal sign, underlying density sediments, higher density sediments of density around 2.4 to 2.7. This leads to the buoyant rise of the lower density materials, leading to what's called salt diapirs. Again, the Gulf Coast diapirism, salt deposition in mid-Jurassic, sediment deposition during the Cenozoic era, and this is like 15,000 meters thick of sediment dumped on top of this salt. And it's created a lot of different things like salt anticlines, salt tongues, bulbs, detached salt stocks, intrusive salt stocks. And in map view, if you take all the trees out, we can see what some of these things look like as they've pushed the crust. So this salt really can deform, also create and deform the sediments above them. And it's really a non-tectonic type of structure. We also have impact structures. I'll again let you read about these, but here's some examples: Meteor Crater, Arizona; Wells Creek structure in Tennessee; Jephthah Knob in Kentucky; Serpent Mound in Ohio; and even in Indiana, in Kentland Quarry, we have an impact structure. If you ever have an opportunity to go up into Kentland Quarry, it's a pretty cool place to visit. So now I want to take a break from primary structures and non-tectonic structures and talk about depositional contacts or types of contacts. Because when we're mapping in the field, one of the things where we collect much of our data is along contacts between igneous and sedimentary rocks, between sedimentary and metamorphic rocks, and within sedimentary rocks themselves. So first we'll start with normal depositional contacts. This is what we typically think of when we're talking about sedimentary rocks, is this formation where one layer is laid down and there's another layer laid on top of it. And this is a conformable sequence. A conformable sequence means that there's not really any time missing between when one layer was laid down and another layer was put on top of it. So conformable deposition takes place during continuous deposition or during separate events so close in time that age differences between the layers are insignificant. The layers are parallel to subparallel. Again, this law of original horizontality kind of defines that they should be parallel to subparallel. Within these sets of layers of contacts or beds, we can define formations. A formation is a set of rocks that are or once were horizontally continuous, that share some distinctive feature of lithology and are large enough to be mapped. Okay, this is a key part for a structural geologist. We map formations. We map things that are large enough that we can trace them from one location to another location. And therefore, we can put them onto a geologic map. A sedimentary facies is the lateral changes in sediment as depositional environment changes. So you could go from a fluvial system, a river system, to a beach system, to a shallow marine system, to a deep marine system. And these are all facies changes. They're all related in time because they're all happening at the same time. But there's this change in the depositional system and their facies. And those things can all fall within a formation. You can have facies changes within a single formation. Another type of contact is an unconformity. Unconformities are a break in the geologic record where some part of the geologic history is missing. So if I look at this first one up here, I have a limestone bed making a conformable contact with a sandstone bed. But then the red line here is representing an erosional surface. So that's an unconformity. And there's a variety of types of unconformities. There's disconformities, angular unconformities, a nonconformity, and a buttress unconformity. And let's take a look at each one of those. Let's start with a disconformity. And what I've done here is I've tried to give you a geological history of disconformities. And you really should start learning this. This is something to put into your mind and as memory as to if I think of a disconformity, what is happening in the geologic history? What are the tectonic setting in which that occurs? So disconformity is an unconformity separating strata that are parallel to each other. It's difficult to detect without complete knowledge of the ages of the beds within the stratigraphic sequence. So this comes back to the geologic time scale, and it comes back to understanding fossil sequences and aging of rocks. And how do we know what rock is older than another? Geologic history, how does this conformity form? There's deposition of a sequence of rock units. There's an uplift or drop in sea level. There's erosion or non-deposition without tilting or deformation of the sequence. Then there's subsidence and renewed deposition. In other words, the ocean comes back in and covers the sediment and starts putting new sediment on top. So we've had deposition, we've eroded away part of history, we've then put more sediment on top. So we have a break in time. Tectonic setting, this is common in platform deposits of stable craton interiors. So right now, if we were to go outside and I were to ask you what is the age relationship between the limestone carbonate formation beneath the glacial beds, you're going to say, well, if you remember anything about Indiana, you're going to say, well, a lot of the carbonate is Silurian to Mississippian in age, but the glacial material was deposited about 10, 15,000 years ago. Well, there's a huge unconformity there. And if that glacial material is hardened into a sedimentary rock, we have a disconformity between the glacial material and the carbonates below. Stable platform, stable craton interior. So here's an example of disconformity. This is a disconformity in the Dakota Formation, red arrow. Note the stream channel that is cut. This is a stream channel. This little shallow thing here was a stream channel that cut down through the sediments here. Actually, you can see all this light gray sediment it just disappears as this cut down through it. And what we have then is the contact right here, that erosional surface is our disconformity. Now, again, if you don't know the age relationships, you're going to say, well, there's an erosional surface, but you need to know a little bit more than just that there's an erosional surface there, because you could have an erosional surface within a formation and everything is the same age. An angular unconformity. An unconformity is separating strata, sedimentary or volcanic, whose attitudes are discordant to each other. In other words, some of the beds are dipping and some are horizontal. Geologic history. You have deposition of a sequence of rock units. Now we have rotation of the layers to shallow, moderate, steep, or overturned dips by folding or faulting. We have erosion. Then there's subsidence or sea level rise, and you have renewed deposition over top of that. This is going to have a tectonic setting of what's called a foreland or active continental margin settings. We're going to talk about foreland and active continental margins later on in the semester as we get more into plate tectonics. So here we have a nice example of an angular unconformity. The horizontal beds, we can trace these beds running across here as nice horizontal units all the way over to here. So I'm going to get my pen. And then we have a series of tilted units. So my unconformity is right across there. Dipping units here, tilting to the right corner of the screen, horizontal units at the top. There's a time period missing where we've eroded off the top of these tilted units, and then we've deposited new units on top, creating an angular unconformity. And the third unconformity is a nonconformity. This is an unconformity in which intrusive igneous or metamorphic rocks, or both, occur below the erosion surface and sedimentary rocks occur above. Again, geologic history, we have intrusion or metamorphism or both at relatively deep levels of the crust. We have vertical uplift, which is raised these things up to Earth's surface. Then there's erosional uncovering of the crystalline rocks. There's subsidence or sea level rise, and then renewed deposition. So now we've taken something, we've eroded away the rock, and now we've taken away time, and now we're putting new deposition on top, creating an unconformity. Tectonic setting, this is again foreland and active continental margins, can also happen in stable continental interiors, platform sediments overlying basement rock. So in this example here, we have the basement granite down here. This is the Fort Bliss limestone, sandstone. Note that this is dipping to the right side of the screen, so this has been tectonically impacted since the formation or the deposition of the Fort Bliss over top of the basement granite. But the nonconformity is that contact between the granite and the sandstone. This is the missing time. Finally, the buttress unconformity. A buttress unconformity occurs when younger bedding is deposited against older strata, thus influencing its bedding structure. And if we look really carefully here, what we're seeing here in the white is a very steeply dipping carbonate. It's almost vertical. The bedding plane is the white. Matter of fact, I'll point at it here with my pen. So that's a bedding plane. And so it's dipping very steeply in this direction, very, very steep. Whereas here, if we trace these beds across, these are nice horizontal units. Sorry about that. So we have horizontal beds coming in contact with beds that have been tilted vertically. So something had to have happened after these were deposited to tilt them very steep, and then for it to start being covered by some later sedimentation in a horizontal fashion. And basically, we've just starting to cover up this bed, this unit. It would be kind of like going to the beach and taking your, I don't know, take your friend and you start burying them in sand. That's the new sedimentation coming in over top of what has been placed there. So finally, one of the key things in the field is identifying unconformities. So what I've put over here to the right, and this again comes from your book, there are some key things you look for in the field to help you identify these unconformities, especially if you're dealing with a disconformity. One of these is channeling, as we've seen. There's been a down cut into other horizontal units. You can get a basal conglomerate. This usually is the result of ripping things up from the rocks below by a current, and then you're depositing these coarser grains along the base. That's an erosional. You may end up looking at fossil evidence. There's a discordance in fossil evidence where you have fossils that are all Cambrian age, and above it you have fossils all Jurassic age. So you know you've missed time. And the others, you may find a soil horizon. If you have the development of a soil horizon, you know that the sediments below have been exposed at the Earth's surface, and sea level rose, and it's all been buried again, so we've lost time. So these are wonderful ways of identifying disconformities, whereas angular unconformities and nonconformities are fairly straightforward. Disconformities are a little more difficult unless you look for some of these key ingredients. So that's it for today. Again, I thank you for listening. Go through this a couple times, start getting some of the terminology into your mind. So again, we can communicate easier. As we move forward, we're going to continue to build on what we've been doing. I thank you again. Take care and stay well.